Hi everyone and welcome to lab 4. So this lab covers the functions which deal with normal distributions. Now the previous lab looked at binomial distributions, and there is some code at the beginning of here that goes over a little bit of additional information, some simplified calculations on binomial distributions. What we're going to do though is just load up tidyverse. I think I already have it loaded here. And we're going to come down to line 91 here, where we start talking about normal distributions. Now, the functions here, you might notice, are quite similar in a way to the ones that dealt with binomial distributions. So all of them have this norm suffix, and then we've also got various different lessers that allow us to do different things with normal distribution. And the ones that we're going to go over here are primarily R norm, P norm, and Q norm. D norm can be useful, but generally speaking, these are the three that we're particularly interested in. Now, to understand what we're doing here, it's useful to think about first some of the properties of distributions. And these are the properties of normal distributions, but they're also the properties of distributions in general. So if we think about a distribution, and I'm going to draw a normal distribution here. So we have a few different things that we can calculate with regard to distributions. So some of these are measures of central tendency. So in other words, let's draw a proper line, shall we? So some of these are essentially measuring, what is the middle observation here, or some measure of how it's sort of centered. Another one, though, is we could have measures of spread. Now, what that means is, let's draw some lines, that we could, say, calculate the mean or the median. For spread, we can calculate standard deviation or variance or range. But for the purposes here, there are two kinds of calculations here that have some special properties. So one is the mean as a measure of central tendency, and another one is standard deviation as a measure of spread. And we can calculate this for any distribution, but that means we can calculate it for normal distributions. And we'll see some of the consequences that has, both in this lab and in some subsequent others. Now, the first thing we're going to look at is R norm. So here is R norm as a standalone function. If I can just copy it out here. And you can see we've got three parameters. So we have an n, so this is similar to R binomial, but we also have a mean and a standard deviation, which you can see we can set at particular levels. So in other words, if we go back to our illustration here, and we can say the mean is 55, and the standard deviation is going to be 15. Let's clean that up a bit. So what we're going to do is we're going to generate 1 million random observations, but we're going to tell it that we want the distribution to be normal, and we want the mean to be 55 and the standard deviation 15. And we're going to save that as norm data. So if I run this, there we go. We can see our data has appeared over here. If I there we go. Let's just get rid of me. We can see 1 million observations of one variable. Now, what happens if we graph that out? What does that look like? Well, there it is. So here's our normal distribution. Now, one thing we might notice about this is the shape here is set by this function, which means that actually whenever we change this to, So let's change this to 555 and 11, for example. Well, the shape of our ggplot here is never going to change. We can have as low a mean as we like, as high a standard deviation as we like. This doesn't change. The only thing that's going to change here is the x-axis. So normal distributions then, like all distributions, have a standard shape. And any different kind of numbers can go into those, but the shape won't change. And this is a really important property. And we're going to be exploring that this week and in some subsequent weeks as well. So here's our normal distribution. Now, if we want, we can check that it's generated a distribution with the properties we want. So we wanted a mean of 55 and a standard deviation of 15. So here we can see we're using this variable, x. And if we calculate the mean and standard deviation of x, what we'll find is numbers very close, but not exactly the same as 55 and 15. So this is randomly generated data, and with quote unquote only 1 million observations, we're going to get to about 2 to 3 decimal points of the exact value here. So we've got a little bit of variance, but not much. So we've generated data that has a mean of 55 and a standard deviation of 15. Now, that's not that useful on its own, but just like the functions that we had for the binomial distribution, there's actually no need to generate this kind of data in order to run calculations on the assumption of normality. Now, what we're going to do to try and understand this is think about a little thought experiment. So these numbers, 55, a mean of 55 and a standard deviation of 15, as the text explains here, this is about normal for a university module. So usually the mean score of students in assessments will be between 55 and 65, maybe a little higher if it's an easier assessment. And the spread will be sort of on average about 15 to 20 marks around that point. So some up in the 70s or higher and some down lower. But it tends to have this structure. Not that many people get low marks, not that many people get high marks. Most people cluster around a sort of average grade here. Now, what if in that situation I wanted to know, well, how well did I do? So we might take a number like 70, right? Most people would be happy with a 70 in an exam. That's the traditional dividing line between two ones and firsts. But what maybe is more meaningful is, well, if I got a 70, how well did I do overall based on how everyone else did? What proportion of people got higher than me or lower than me? Now, this is what this function pnorm does. So p here for proportion, but we could also think about it as probability density. Although this is an idea that we'll be going more into in subsequent weeks. Here we're assuming we have all the data, but we will be able to use this same logic to think about probability. Now, what you can see is that pnorm here, rather than n, here we just specify a number. And that's a number in the same units as we specify the mean and the standard deviation is. So let's think about what that looks like visually. So if we say that we have here a line around here, and that this is what we call our x value, and that's 70. So we specified 70, a mean of 55, and a standard deviation of 15. And we'll come back to this lower tail thing in a moment. So if we run that, what answer do we get? Well, we get 0.158. Now, what does this mean? Well, in this configuration, with lower tail false, what this is going to tell us is the percentage of people in a normal distribution with these qualities who scored above this level. And graphically, what this looks like is that it's just the area under this part of our normal curve. So in other words, this is about 16% of our overall distribution. We could say sort of 15.8, but let's summarize that as about 16%. Now that, of course, means on the other side that this area, sort of the whole rest of the area under the curve, well, that is roughly 84% of the distribution. So just by specifying this cut point, then it's going to tell us the area above this. Now we can, of course, calculate this. So really all we're doing here to calculate this is that we are calculating 100% minus 16% equals 84%. Because the whole area under this curve has to sum to 1. Right? These are all our results. Has to sum to 1 or has to sum to 100%. Now this lower tail then, this just specifies which side of this 0.70 we're interested in. So if I set this then to true, if I can spell true correct, if I set this to true, what we will get is, there we go, just over 0.84, which of course we could translate to 84%. Now, of course, we could do this the other way. So we could have lower tail true here. And this time we're going to calculate this and subtract it from 1. And of course, this gives us the inverse. So lower tail false, 15.8, 16%. Lower tail true, subtracted from 1 is also the same thing. So that area under the curve sums to 1. So we just need to calculate one part of it and subtract it from the other. Or we change whether we set lower tail true or false. Now, you might wonder, why do we call it lower and upper tail? Well, that's just because really it's just lower values on this side. So this is our lower tail. This is our lower tail. And this is our upper tail. Now R uses this kind of true false language, so we tend to use lower tail false means upper tail, lower tail true means everything on this side. The interesting thing is here, though, that we can really put any numbers in we like here. So say, for example, I'm going to say lower tail false here. So I want to know how many people got above me. What if it was a different assessment? So, a 70 is a 70, we might say, but it might be more or less impressive on different assessments. So what if instead the mean score on this assessment was different for this one? It's a 60 rather than that. Let's keep standard deviation the same. Well, my 70 is a bit less impressive if the mean overall is 60. It means I'm actually only in the top quarter of the class rather than the top 16% here. So we can compare scores across different distributions with this logic. We can actually do something even more, though. So one thing we can do is we can actually compare entirely dissimilar systems. So although this is one university mark in this example, we don't have to use that, because we can still say the same thing about where an individual falls in a distribution, no matter what the unit of measurement is here. The second thing we can do is we can also translate any of these positions, so say 70 on a distribution of mean of 55 and a standard deviation of 15, to something we call the standard normal distribution, and represent it with something we call a z-score. Now, this is a little unintuitive at first, but let's think about the logic here. So let's first think about what is the standard normal distribution. Well, the standard normal distribution is just a normal distribution, but it has two special qualities. So if I can draw a normal distribution again. So on a standard normal distribution, the mean, so this central line here, and the standard deviation always have these figures. So the mean on the standard normal distribution is 0, and the standard deviation is 1. Why is this interesting? Let's look back at this. So one thing we can do is we can transform scores like this on these distributions into something we call z-scores. Now, the calculation for a z-score is actually pretty simple. The calculation for a z-score, if we come back to here, is that we just take the score, so our x, subtract the mean, and divide by the standard deviation. So if we think about our previous example, that's going to be 70 minus 55 divided by 15. So the z-score here would be 1. Now, what is that z-score? Well, what it is that it is the representation of the relative position of that 70 on this distribution in terms of the standard distribution. So our x, in this case, becomes a z-score of 1, which means 1 standard deviation from the mean. So if our z-score is 1, we're 1 standard deviation from the mean. And crucially, 1 standard deviation from the mean also means a set percentage on this side and this side of the distribution. And as we already saw, that, in this case, was 16%. So a z-score of 1 will always mean that 16% of the distribution will be higher than where we are, and roughly 84% will be lower. So how is that helpful? Well, let's think through this example. And let's try and compare two individuals, or maybe the same individual at different points in time, on two very different scales. So let's think about university marks again. So we're going to keep our mean of 55 and our standard deviation of 15. And this time we're going to use R norm to generate 1,000 random instances, or 1,000 random observations that have these qualities. Let's also, though, generate some GCSE grades. So as some of you will know, GCSE outcomes in the UK are from 1 to 9. So what we're going to say is, let's imagine that mean is about 5, the standard deviation is about 1.5. And again, we're going to generate 1,000 observations. So we have GCSE scores and university scores. Now let's imagine and read into our code on R. And again, I'll just get rid of myself so you can see what we're reading in here. So our GCSE student is going to have a score of 8 and our university student a score of 75. So you can see this is appearing in our environment over here. Well, what happens then if we convert these scores to their Z scores based on these respective means? So here I'm going to calculate the Z score for the GCSE student. So here's their grade, subtracted from the mean of all GCSE grades, divided by the standard deviation of all GCSE grades. And here's the university student with exactly the same calculation. So let's run that. And we can see over here, so now we've got Z scores for these two students. So the GCSE student has a Z score of 2 and the university student of about 1.3. Well, let's go back here and see what that means. I'm going to debloat this graph a bit. Let's get rid of all these calculations. Okay, so we know the standard deviation of this distribution is 1. So 1.3 then, let's say that puts us about here. Here's our university student. So they had a Z score of 1.3. Our GCSE student, however, they had a Z score of about 2. So we put it out here. This isn't really properly to scale, but I'm bad at drawing. So GCSE equals a Z score of 2. So in other words, then, only this proportion here are greater than our GCSE student, but all of this proportion right out to here scored better than our university student. The conclusion then is that this higher Z score means the GCSE student is overall doing better within their distribution than the university student is. Now, if we go in the other direction with our Z scores, so let's say this is a standard deviation or a Z score of +1, +2, and actually this should have within this distribution up to about +3. Here we have -1, -2, and -3. So if we decrease the scores of our hypothetical students, so let's give the university student a 40, GCSE student a 3. Let's recalculate those Z scores. See, now we've got -1, -1.3. So in this case, right, it's the GCSE student that's doing a bit better. We could plot this on here by saying, so our university student is, what was this about? At a Z score of about -1. And our GCSE student this time was at about, let's say, -1.3. So in this case, then, it's the GCSE student that has, the university student rather, is doing better than everything up to here, whereas the GCSE student is a bit lower down the distribution. They've got more people ahead of them. So these Z scores then can be used to compare the position in the distribution across different distributions or different units of measurement. so long as that distribution is assumed to be normal or roughly normal. And it can do that in a single number. So a higher z-score, whether it's positive or minus, always puts you higher up the distribution as an observation. But we can start from numbers which relate to concrete distributions. So about 0 to 100 for university marks, 1 to 9 for GCSEs. But we can still rank these students against each other. Now, there are a few more distribution functions, normal distribution functions in R that we can use. And I want to particularly look at QNorm. Because QNorm, really all we're going to do is, we're going to take the calculations that we already ran, and we're going to do them backwards. So let's erase this and we'll recreate our previous graph. So we have our normal distribution. It's got a mean and a standard deviation. And previously, we specified a point on here that we called x. But actually, there's no need to do it this way around. Because what if instead we said, well, I'm interested in this value instead. So let's say that our x here was a mystery. So before we specified this to be 70, this time we're going to leave this blank and say that instead what we know is that we want 84% of the distribution to be lower than whatever our mystery value is here. Because this is the same calculation the other way around. If we know this and we know this, using our x value, we can calculate this figure. But if this is the figure that we know or are interested in instead, we can use that to calculate x. So what does this look like? I'm going to skip over dnorm here, and I'm going to come down to qnorm. So let's set up a qnorm with the figures that we've been using. So qnorm, instead here, we specify this 84%. And let's give it that mean of 55 and the standard deviation of 15. So if we run that, we can see we've got an answer, which is basically 70. So this was rounded, as you remember. So we've not got quite to 70, but it's around 70. So this time then, we've started with the notion that we want 84% here. And we've calculated that this value is 70. Now lower tail and upper tail does also work here. So if we specify lower tail to be true, lower tail to be false rather, we're going to get the inverse value. Now, what is that inverse value? Well, essentially, all we're doing is saying that we're interested in the 84% on this side, with only this part remaining. So, in other words, this 84%. So where is our x value there? Well, we just calculated it to be at about 40. So our x here is 40. So we can do this either way around then. You know, the distribution, normal distribution is symmetric. So we can calculate the 84% of the upper part of the distribution, giving us an x of 40. versus the 84% of the lower part of the distribution, which would give us an x of 70. Of course, this part is likewise about 16% of the remaining distribution. So what would we practically use something like this for? Well, we might say something like this. So imagine that I had student groups that I was giving a task that I knew on average would take around 10 minutes. I also know that those groups would finish the task with a standard deviation of 1 minute. So say I've calculated this from previous groups. Now, a useful thing I might want to do then is to say, well, how long do I have to wait until 99% of groups are finished, assuming that we've got this normally distributed shape? Well, I just have to plug the numbers in. So here's my mean of 10 minutes, my standard deviation of 1 minute, and then I specify that I want 99% of the distribution to have finished. So back in this example, let's get rid of all of this again. And I'm going to fill out these numbers here. So here we go. We've got a mean of 10, a standard deviation of 1, standard deviation is 1. And what I want is to have 99% of my distribution to be already filled in. So all of this I want to be filled in. So we'll call that 99% of my distribution. So in other words, what here is my x value? How long do I have to wait before 99% of my student groups are finished? So if I plug in the numbers here, 99%, a mean of 10, and a standard deviation of 1, there's my answer. So 12.32 minutes. In other words, this x figure is 12.32. Now, those are really the only useful functions here with normal distribution. And these functions are not ones that you would use very often in real analysis. However, as we'll hopefully see in the weeks that are coming up, this basic logic of areas under curves has a lot more uses than just this. Because what if we imagined that instead we had, for example, two distributions? So if I had one distribution here, one distribution there. Now this would give me two group means. So one group mean would be here, and one would be here. Now again, say these are university scores. So let's say that the mean of this group of students in their assessment was 55, and the mean of this group of students was 65. Now, did this group actually do, on average, better than this group? Now, we could say, well, yeah, that's a 10-point difference. But actually, the reality is that whether this is significantly different depends on the respective standard deviations. Because actually, there's quite a bit here of overlap. And if these were samples, it's possible actually that the real underlying mean, say of group 1 here, maybe it's somewhere around here, and that the real underlying mean of group 2 is somewhere around here. It's even possible that, in fact, this is the mean of the group that I calculated of 55. And this is the mean of the group I calculated at 65. And this logic is where we get the idea of statistical significance from. To do that, though, we're going to have to do some more complex things. We're going to have to do things like calculate p-values from that same logic as generating z-scores. But ultimately, this is going to allow us to make some more sophisticated inferential judgments about whether two distributions differ, what is a significant difference between one number and another, and ultimately, when we get to correlation and regression at the end of this course, we're going to look at this same logic being able to tell us, well, is a relationship between one variable and another real and reliable based on our sample? But that's all to come in the next couple of weeks. This normal distribution functions, these will come up in the assessment, but nonetheless, what they really are is building blocks to being able to understand some of the logic of the statistical tests that we're going to look at in a few weeks' time. So I'll leave it there. Next week, I think we're going to be using, again, this same logic to look at things like confidence intervals and some slightly different kinds of distributions. So I will see you in the labs this week, and I will see you in the next one of these I record.